Last week we talked about the background and design issues. They were 1. The inclination of the towers, 2. The height of the sky park, 3. The cantilever construction. Today we're going to talk about the foundation and excavation of the Marina Bay Sands. In weeks 4 till 6 we'll talk about the construction of the hotel towers. Next, the construction of the sky park and other things such as the atrium, facade, material, etc. Finally, we review and summarize the project. However, this schedule can be changed depending on the progress. This presentation consists of 3 chapters. Let's start with the introduction to the foundation and geotechnical aspects. As for every building, the foundation is one of the most important compartments to make a good construction. The soil of the project caused quite some challenges. The construction started on the 17th of January of 2008 and took about 6 months for the basement and foundations. This is a very short time relative to the size of the building. This table shows the excavation plan and excavation depth. As there was a highway located right next to the construction site, it was quite difficult to move construction vehicles and transport materials. Years before the construction of the Marina Bay Sands, there was a disaster for a project nearby, the Nicole Highway collapse. On the 20th of April 2004, the Nicole Highway accident killed 4 construction workers and injured 3 others. It was caused by a tunnel excavation construction nearby and caused the collapse, creating a gaping hole in the Nicole Highway. The reason of the collapse was because of the composition of the soil in Singapore. The ground was made up to 4 meters of marine clay. This soft soil was too weak to support the heavy road and caused a lot of horizontal pressure. As construction progressed, movement of the soil occurred and eventually caused the struts of the construction to collapse, resulting in a lot of damage to the project, the loss of lives of the construction workers, and a lot of cost. This incident had alarmed the progress of the construction of the Marina Bay Sands, and as a result, during the excavation phase of the construction, about 2.8 million cubic meters of fill and marine clay were excavated from the site. This amounts to 800 trucks every day for the next 2 years. Let's start with the site analysis. This project is located on reclaimed land, which is a land made by making embankments on the seashore and taking water out of it and filling it with soil. The Marina Bay area had several phases of reclamation. The latest one was completed in the mid-1990s. The Marina Bay Sands sits on this latest reclamation zone, which led to many problems for the project's construction. Let's take a look at the site's geology here. The cross-section along the CC line, shown on the right, represents the soil profile of the hotel towers. The section consists of sand infill overlying soft marine clay above an underlying very stiff alluvium layer. The blue layer consists of soft clay called kalang. It was too soft to support the huge weight and caused significant challenges to the excavation works. The bottom layer is the alluvium layer, which is a hard layer that was deposited for over a long time under the weight of the marine clay layer and was suitable to support the weight of the structure. In short, the Marina Bay Sands experienced the following problems during the excavation phase. 1. Weak soil. The ground was too weak because it was newly created. 2. High soil pressure. Due to the high water table, a high soil pressure was continuously applied during the construction of the foundation. Then, how to overcome both problems for the foundation construction. To overcome the weak soil problem, a lot of barrettes and board piles were inserted into the alluvium layer. Unlike the conditions in Korea where a 10-meter excavation would reveal the base rock, this site required the foundation to be 40 to 60 meters underneath the ground. To confirm the load capacity of the pile and barrette foundation, the so-called Oosterberg, in short, OCEL technology test method was used. Load test programs using the OCEL method can confirm the load capacities. The OCEL method was chosen for the following reasons. To confirm that the design loading requirements were being met, for its ability to isolate and load the foundation bearing strata, for its ability to separate the end bearing and the skin friction components, and for its ability to provide high test loads even with the deep foundation cutoff levels like 40 and 60 meters underneath the ground. This table compares the advantages of the bidirectional load test with the conventional method. We know it's a way to save money, time, and even check stability. The oat-cell method works as follows. Before the reinforcement cage is placed in the pile or barrette, the cell plate and several sensors at different intervals are attached to the cage. After the foundation is completed, it's possible to monitor the actual behavior of the pile and confirm the loading capacity. The next problem was the high soil pressure. In the excavation phase, a lot of temporary struts need to be used. However, struts make it difficult for the excavation and construction. To overcome this problem, the engineers applied the circular diaphragm wall method. Conventional rectangular shaped walls have to be supported with steel struts to prevent the wall from collapsing. However, this circular diaphragm wall didn't require any internal supporting struts. So this method can remove the temporary struts and can reduce the construction time. This experiment shows that the round-shaped cofferdam is stronger in pressure than the square cofferdam. This is because, for circles, the force is evenly distributed along the wall. The 120-meter diameter cofferdams were among the largest to be ever deployed in Singapore, and are notable for their excavation depth of 80 meters below the ground. They allowed work to progress across the site simultaneously, with either the excavations to the north or south being able to be in advance of each other. Jet grouting is a ground improvement or soil stabilization method. It can provide convenient solutions for the most of the geotechnical problems. So the engineers used the method for the Marina Bay Sands Foundation. The process of jet grouting is as follows. First, the area where the soil has to be treated is chosen and a hole is drilled into the required depth by a rotating drilling system under high pressure. Then the equipment is placed over the hole and injection process is continued. Now the main jets start. The string is raised and rotated slowly to seal the wall column surface with soil and fluid system. Then the grouted fluid is hardened within the soil, forming bodies called jet columns or jet grouted columns. The completed jet columns can act as horizontal barriers to control the groundwater, underpinning to stabilize foundation systems, earth retaining systems. Depending on the type of soil to be treated, one of the three variations is used. Type 1. Single fluid grout plus water and cement. Type 2. Double fluid plus air plus grout. Type 3. Triple fluid plus water jet. Let's take a closer look. The drill system drills to the required design depth. The main jet starts and erodes the soil around the jet column. The method of jet grouting was used to create the circular diaphragm walls. This week, we discussed the foundation and excavation works for the Marina Bay Sands. The two largest problems for the foundation were the high soil pressure and the weak soil on the reclaimed land. In short, to overcome these problems, the engineers used the circular diaphragm walls to make a large excavation to withstand the high soil pressure. And within the excavation, they constructed the foundation barrettes, piles, and basements to distribute the force into the hard alluvium layer. Next week, we'll talk about the construction of the hotel tower. Thank you for watching.